Hello and welcome again to my Physical Science online video lecture supplement series. In today's video, I wanted to, with the help of the Colorado PhET team's geometric optics simulation, explore a little bit of one of the labs that I am doing. Specifically, we are here to talk about the lens lab, walk through a few calculations, examples, and maybe some discussion of the lab to help all of you who are attempting this from home. So let's start off by pulling up the lab instructions. So here is the first part of the lab instructions, and you can see that there's a link here to a simulation from the Colorado Physics Education team. We're going to use that in just a minute to help us with this lab. Before we get to that, we have our equipment list. So you're going to want all this stuff if you're going to do this lab. A positive converging lens. Before anything else, I should probably mention that you are going to want a specific type of lens, because a lot of people like to go out and buy those reading lenses that are made for sort of reading a book. They're like a reading magnifier. Those are nice and all, but they are actually what's called a Fresnel lens. And the type that you really want is more of a spherical lens. So what do I mean about those two things? If your lens looks basically like this, then you are doing what you're supposed to be doing. Any of these simple magnifying glasses, like what you can buy at the store, Walmart carries them, as do a variety of other grocery stores. You don't necessarily have to go to the eye doctor to get one of these. Okay, so from the side, this right here is the kind of lens shape you want. It basically has a smooth bulge. It looks like it could have been sliced off the end of a sphere, and then one side can be flat. That's fine. This is a spherical lens. The one that's right beside it is what a Fresnel lens looks like from the side. And basically what it is, to open up the picture that they've got at the Hyperphysics site, which is a nice site for those of you who are looking for more resources. Basically what you do with a Fresnel lens is it's sort of like you take some little slices from the surface of this spherical lens and then you kind of flatten it out. So it's a much thinner lens, and the result is that you get a poor quality focus. It's basically going to be a lens that looks more or less like this. This looks kind of like the sort of lens that you might use for reading. So any of these reading magnifiers that you get, and especially the ones that you can kind of fold or that are flimsy, these tend to be Fresnel lenses. And in fact, the big hint that they are a Fresnel lens, what Fresnel lenses do is they allow you to sort of simulate. This one probably is actually a regular spherical lens. They allow you to approximate a spherical lens, but to do it with a much thinner piece of material. And that works nicely if you're trying to do something like read a book, or for that matter, if you want to collect a lot of sunlight to burn something, as that previous image was showing. But the problem with the Fresnel lens is that at times the image quality might suffer a little bit. And so I think you're just gonna have better luck here if you use a simple spherical lens, just so we're all basically on the same page. So that's today's caveat and today's sort of aside on how lenses are built. So let's look at the experiment itself. There's three basic ways that we're going to be measuring the focal length of your lens. So you're basically looking to figure out how long is the focal length of the lens. So let's go ahead and draw a rough diagram of what this focal length looks like. Let's say that you have some rays of light which are coming in collimated. That means basically that when we draw these rays like this, they are all parallel to each other as they approach the lens. So this looks like basically a beam of light. When they get to the lens, basically what happens is they refract through the glass. So this one right here is actually roughly on the principal axis, so it doesn't really refract much. These two are off axis, they refract a little bit so that they can cross somewhere, and this point at which they cross is called the focal point. So this is the focal point. Oops. Point. And this distance between the focal point and the lens is labeled F, is the focal length. And so this right here is the thing that we're actually trying to find in this lab. And you'll see, by the way, if you add some additional rays in here, that they will also start off parallel. They will also deflect. And whoops, I'm actually drawing them so that they don't quite deflect to the same point. So in this case, the focal point is usually defined as the point at which the combination of rays is the smallest. And the fact that they don't all cross in the same place is called aberration. And aberration is a topic of interest in optics. It's a topic of interest when designing lenses. It's a topic of interest in correcting vision, etc. There is always some small spherical aberration even from a spherical lens. The Fresnel lens often tends to have slightly worse aberration than a spherical lens. So that's one more reason why I want you to use a standard spherical lens magnifying glass rather than just a reader. Okay, so as I said, there's actually three different methods that we use to try and figure out what the focal length of your lens is. The first and easiest is that you use a collimated light source. And so the collimated light source I already drew the ray diagram for, means all the rays are basically parallel. If it's a sunny day outside when you're trying to do this, then the sun is an excellent example of a collimated light source. It is effectively a point object given how far away it is from the Earth. So we're far enough away that it acts like a point object, except for that the rays coming from it are virtually parallel. So usually a point object is not a collimated source. Usually the rays leave in a spherical shape. But because we are so far away, any rays which are incident on the Earth are roughly parallel to each other. In other words, we're taking up a very, very, very small fraction of the surface of the sphere into which the light from the sun is radiating. Okay, so what we do with this one in any case is you hold up your magnifying glass, being careful, by the way, to not back reflect some of the light into your eyes. You can actually hurt your eyes doing this if you're not careful. And then you should have a simple index card that you're focusing the sunlight onto. And basically what you do is you move the index card until you get the smallest spot from the sunlight on the card. Now, mind you, if you rotate the lens a little bit, you'll sort of deform the spot size. So you're going to want to hold the lens pretty close to being perpendicular with the incident rays from the sun to get the smallest spot size possible. And what you want to do is you want to see where is the light focused to a point. So here's my rough attempt at illustrating what that looks like. So here's the collimated rays. They're entering into the magnifying glass. They focus down. If you happen to put certain objects, paper usually will work fine, sometimes even wood, that kind of thing, near the focus, it'll actually start smoking because you get the light intense enough that you can kind of burn a little bit of the paper or the wood or what have you. And in fact, you can do this to start fires. This is one way of starting a fire with no matches, if you will. In any case, you want to figure out what the distance is between your magnifying glass and the thing that you're projecting this sunlight onto. That distance is your focal length f. Now you'll notice when you do this that there's some range at which you can hold your piece of paper, your screen, your board, whatever, over which A, it looks like you have a very bright small spot, and B, over which you observe smoke. So you might be able to hold it here and get some smoke coming out. You might be able to hold it out to here and get some smoke coming out. So the actual focal length then that we might use is basically the average of these two, which we represent with an F with a little bar over it. And so that would be the point that is midway between these two boards, or these two screens. Okay, and so this distance between the two is called the uncertainty. So this might be called delta F, is the uncertainty. And actually what this is it's twice the uncertainty. Because your range over which you get this smoking are basically F minus delta F and F plus delta F. So if you hold the board any distance between this one and this one away, you will notice that it smokes, or you will notice that you have the smallest spot size. So let's say that you have, as an example, you have your board, and at, let's say, 24 centimeters, it starts smoking. So 24 centimeters away from the lens, it starts smoking. Let's say again at 26 centimeters, it stops smoking. And so what this means is that your average guessed focal length is the one midway between these two, would be 25 centimeters. And your uncertainty in focal length is 1 centimeter. So your range over which it smokes is 25 centimeters minus 1 up to 25 centimeters plus 1. This one you notice is 24 centimeters. And this one is actually 26 centimeters. So that is how we find our range the easiest way. Now note again that you may actually use something that doesn't smoke. You can always just look and see when does the spot happen to look like it's at its smallest and brightest. And in fact, if you have something that doesn't burn, you may be able to narrow this range somewhat. You may be able to get it below plus or minus 1 centimeter. You may be able to figure out that it is in fact at 25.2 plus or minus 0.3 centimeters or what have you. So pick your materials wisely. The second method that we use is pretty similar to this first method in that you should notice if you move your screen away from the focal plane that what you get on it is what looks like a very bright circle, and then if you look very closely you might see rings around the circle. The bright circle basically represents the the image that you're making of the sun on the screen, or what the sun looks like as imaged onto that screen. It won't necessarily be in focus, but you should in fact see a bright circle of some size. So what you do is you pick, in this case, a size, maybe an inch, for example. So your magnifying glass is 4 inches apart. You want to know, where is it 2 inches, or excuse me, where is it 1 inch apart, or where is it 1 centimeter? So you mark the 2 places where you push your screen to get that. Okay, so here's your focal point. Maybe you put the screen here and you put the screen here. So this one will mark as 1, this one will mark as 2. And on number 1, if you actually look at the screen, you see that the spot is like this. So you have some bright spot, and what you do is you measure how big is this bright spot. Let's say that it is, we choose 1 centimeter. So you measure that the spot here is 1 centimeter, and then you pick a second spot, a second screen where this is the case. So both of these basically show the same image of a spot that's 1 centimeter long. So let's say that the 2 distances in question are given by maybe this is, call it D1, and this other one is D2. So those are your 2 distances. Well, then the focal length is actually going to be the average between those 2. So it's going to be D1 plus D2 divided by 2. So to use an example, suppose that this spot appears when, so at D equals, let's say 20 centimeters, have a 1 centimeter spot. And then at D equals 28 centimeters, have a 1 centimeter spot. If this is the case, then we can say that the focal length is 20 centimeters plus 28 centimeters divided by 2. So 20 plus 28 is 48, divided by 2 means that we've just measured the focal length to be 24 centimeters. Okay, so this is the second example then. Before moving on to the third method of determining the focal length of this lens, I should say that the safety note I made earlier about being careful about reflections is especially important here, because if you're focusing light and then you're trying to measure the light with a ruler, even if the ruler is plastic, let alone if it's a metal ruler, you're going to get reflections off that ruler. And those reflections are going to be very bright. You know that if you stare at the sun, you can damage your eyesight. Well, this, because you're focusing the sun a little bit, means that it's going to appear even brighter. So if you reflect it into your eye, it's going to be even worse than staring at the sun. So you run an even larger risk of damaging your eyesight if you do this not carefully. I would recommend, therefore, that when you do this measurement, if you have a wooden ruler or a wooden meter stick, that you pick that to do the measurement with, and not a shiny reflective metallic one, or for that matter like a clear plastic one. Those will both reflect pretty badly, and you can actually damage your vision if you're not careful. Okay, so with that safety note aside, let's look at this third method. So the third method is actually the longest method, that's sort of the most complex. You can see as I scroll through here, it's the last probably page and a half or 2 pages of this experiment. What we're doing here is we're using the lens maker's, the thin lens equation. So the thin lens equation basically says if you know the object and the distance, the distance between the lens and the object and the distance between the lens and the image, then you can get the focal length. Really, if you know any 2 of these 3 variables, you can get the third one. So let's look at another simple example of that, just to be sure we're on the same page. Let's say that you have an object that you're trying to image. Maybe it is a candle, and you place your lens somewhere. Usually, by the way, you place the object, you pick some point on the object that you choose to represent the sort of point that you're imaging. So this line right here continues, straight, because it sort of goes through the principal axis. This one right here can do something like that, and lo and behold, you get an image of the object. So this right here represents the image distance. This right here represents the object distance, and the focal length again is determined by, if you have parallel rays coming in, where those rays converge. So let us say that you know both of these. This one right here maybe is 20 centimeters. Maybe this one right here is 10 centimeters. So 1 over dO plus 1 over di equals 1 over f. So we have 1 over 20 centimeters plus 1 over 10 centimeters is equal to 1 over f. This right here is basically 0.5 inverse centimeters. This one is 0.1. 0.05 plus 0.1 gives us a total of 0.15 inverse centimeters. So basically what we do now is we calculate the focal length by inverting. So if you want, we can do the whole thing on the calculator. 20, and if you invert it you get 0.05. That's where this guy comes from. Plus, and then we're going to invert the 10, get you the 0.15, and we invert that, and it's 6.6 repeating. So that means that the focal length right here is about 6.7 centimeters. So we just found what the focal length is based on where the object and image locations are. Now, to see this as a full lab here, we actually can change the location of the object with respect to the lens and then measure where the image will be formed with respect to the lens. I recommend, by the way, that when you're doing this at home you use something like a candle, because it will form a pretty nice image. Basically, you can look on a screen and at some point you will actually see what looks like the image of a candle. It may be upside down. That's another word for that, is inverted. But you'll see a sharp image, and that's where the image is being formed. So then you measure the distance between the screen where that sharp image is formed and the candle itself, and that gets you the DO and the DI. This is the distance to the candle itself. This is the distance to the screen where the sharp image is formed. So you're actually moving the screen position until you find a sharp image. So to sort of guide you through this, I wanted to make use of this simulation that the Colorado Physics Education team put together. So this simulation is called Geometric Optics, and so clicking the simulation launches this link. Basically, we're going to click the play button because that's going to open this thing up. It says move me. So this right here actually represents the object. This right here actually represents the image. And what I want to do here is let's have we can show, I don't really want the guides, I want the ruler, and we can, maybe we'll just have the virtual, the image. I'll go ahead and click show virtual image. Don't worry about that just yet. We'll see what that is in a minute. Second point, if you apply the second point, it just is showing here's some random point on it. I'm going to move it to the eraser. Here's the ray trace for the eraser. Here's the ray trace for the tip. And here's where the image of the eraser is. It's formed from the ray traces. Here's the image of the tip. It's formed from the ray traces. I'm going to go ahead actually and take the second point off, but you can play around with keeping it. It maybe is distracting for my purpose, but it can be fun for yours. What we're going to do is we're going to measure a few things here. So where is the pencil located? It is currently at a position, if I can line this up nicely. So this is 140, 160, so this is 150 centimeters. So I've placed the pencil at 150 centimeters. This is the distance to the object. To keep track of all this, I'm going to go ahead and actually enter this information into an Excel sheet. So let's say object distance, and I'll put in DO to represent that, and note that it's in centimeters. And then I'm going to find the image distance, and that is DI, also in centimeters. Alright, so I need to measure what is the distance to the image, and you can do that on here by basically trying to place this meter stick and then measuring out where is this lined up. So this is again at 150 centimeters. So that's that piece of data. What I'm going to do now is I'm going to pick a few different object distances, and let's say that I am going to go in increments of 10, for example. So I'll put in 160, I'll put in 170, I'll put in 180, and actually I kind of want to go the other way as well. So I'm going to go ahead and move this stuff down here out of the way, and we'll have a 140, a 130, a 120, and a 110. And this gives us, if you're keeping count, gives us the 8 pieces of data that we need. Because in the instructions here in the lab, it says that you want to do all of this for 8 object positions. We want 8 to 12 data points, so just to sort of get all possible ones, maybe we'll do 90 and 100 as well. So that gives us all 10 pieces, gives us 10 locations. I'm not going to go below this for now. We'll see in a minute what happens when I do that. Okay, so let's put our meter stick in position here, and I'm just going to put the meter stick so that it is located sort of centered here. The pencil, you can see, is at the 50 centimeter mark, but this is at the 200 centimeter mark. So I'm going to move the pencil by 10 centimeters and put it at the 40 centimeter mark here. Whoops. So this is 40 from 200. This is 160 centimeters that we're at right now. So how far away is the pencil's image being formed? Well, we stick this guy here, and we have to sort of look, and there we go. It appears to me that it's crossing pretty close to the 142 centimeter mark over here. Okay, and I'm basically just trying to guess where the edge of this pencil is lined up here. So in fact, maybe even a little less than 142, maybe it's 141. I'm going to go with 142 just because that's sort of my first measurement on it. Let's go ahead now and move this guy another 10 centimeters, which is about right there. So this is now 170 centimeters away from the lens. And if we put this in here, maybe we can try to measure it using the guide point, which seems to be pointing about here. This was 140, so this is 138, about 136 centimeters. Okay, now we move the meter stick back over here. It'd be kind of helpful if I could have 2 meter sticks so I didn't have to move it back and forth every time. Try to line this guy up at the 20 centimeter mark, which basically is equivalent to saying that I'm lining him up 180 centimeters away from this. And we now can put this guy in here. Looks like we're lined up pretty close to the 130 centimeter mark now. So now I've moved it to the 190 centimeter mark, and then we're going to stick this guy over here and try to see what we can measure here. Looks like the pencil is just shy maybe of 126, if you will. So maybe we could estimate this as 125 point something, 0.8. This is kind of harder to do with the mouse than it looks. And where's our image formed now? It seems to be formed at just shy of 122 centimeters. In fact, looking a little closer, maybe it's more like 121 centimeters. Okay, so now I have to basically move this thing closer. So let's put this guy over here. We'll move this guy to the 140 centimeter mark, which is roughly there. And let's see, where is the image being formed. You notice that it's now farther away. So in fact, it looks like it is touching about midway, maybe closer to this one than this one. It's 160, call it 163 centimeters. So now let's do from the from the 130 centimeters away mark. So we'll move this guy on over here, and looks pretty close to 180 centimeters. And let's do 120 centimeters, and let's see what we can measure over here. Is actually a little farther than the meter stick. So if I had a way of marking the screen, it'd be helpful. Looks like maybe an extra 6 centimeters or something beyond the length. So given that if I move this thing farther away, it gets closer, and if I move it closer, it gets farther away, I would say that at this point there's no purpose in trying to get the image position as I move this thing closer. So I think we'll call it good with the number of basically data points we have, which is 9. By the way, you can change the thing that you're imaging if you'd like. In fact, it may actually be arguably easier to use the arrow than to have used the pencil, simply because there's nicer contrast with the meter stick. See, this has a better contrast than black on black. I can see that it's pointing right here as opposed to having to look. This is 170 centimeters for what it's worth. This right here, if we stick this guy in on the end, is, thanks to the contrast, you can see that is basically pointing just a little off from the 64 centimeter mark. So subtract that from 200 and it's a little off from the 136 centimeter mark. Okay, be that as it may, I think we're done with taking the data with this simulation for now. I want to turn to actually analyzing it. What we're supposed to do is graph the inverse of the image distance to the inverse of the object distance. So 1 over di versus 1 over do. So let's look at what that is. I'm going to go ahead and put in a graph. So I went to Insert. Here is Charts. The one I want is the Scatter chart. So I select Scatter chart like this. What I want to do is have inverses here. So the inverses, basically, we would put like do. This would be like a 1 over do. And so the units would be per centimeter. And this one right here is 1 over di, and that's units of 1 over centimeters, or centimeters to the minus 1. And so what I'm going to do here is I'm going to say this is equal to 1 divided by this. Equals 1 divided by this. Okay, and this one is going to be equal to 1 divided by this one. And now to fill all that out, I highlight these two and I push Control D, and so that fills these columns downward. Now I'm actually ready to select my data. So again, I'm right clicking on the graph, I'm clicking Select Data, Add, come on, push the range that I need. The range is right here for the inverse object distance, and then this right here, the y-axis, this range is 1 over di. Now I have a nice graph here. What we see here is that this plot of the inverse of do versus the inverse of di that I created has made basically a straight line. And that straight line has a slope of -1. As it turns out, if this was a perfectly ideal situation in which all the measurements were exact and we have an ideal thin lens, this equation actually should say y equals -1x plus some number here. The number is the intercept. So in the ideal case, this actually is that the y represents 1 over di, x equals 1 over do. So y should be di should, 1 over di should equal -1 over do plus some constant number here. This constant number here, if you look at the formula that we're using for all of this, is that we have 1 over dO plus 1 over di is equal to 1 over f. So if you rearrange this formula, 1 over di should be equal to minus 1 over dO plus 1 over f. So this right here was what we had as our y. This right here is what we had as our x. The fact that this is just minus 1 over tells us that this 1 right here is in fact also our slope. So this right here represents our intercept b. So this is the y-intercept from the graph. So pull up this graph again. This was our y-intercept value. So I'm going to go ahead and make two new columns, two new rows here. The first one is going to be my 1 over f row, and that's inverse centimeters. The second one is going to be f in centimeters. So 1 over f I'm going to do by just reading off this number. There is a fancy way of pulling this data out of the data set using what's called the linest function, but I don't want to go into that today. So I'm just going to type it in from what I see on the graph. 0.0133. This right here, since this column represents 1 over f and this is f, this one is 1 over this one, which means that this one is also 1 over this one. So I can go 1 over this. And I have now the focal length of this simulated lens, 75.188 centimeters. If I open this thing up here, these little X's on here actually represent the focal point for this lens. So if I measure from the lens to one of the X's, I see that in fact it is pretty nearly 75. So this worked out pretty nicely. There is a kind of for what it's worth comment here about specifying lens power. So this is really just kind of interest for those of you who know that your eye doctor maybe specifies the strength of the eyeglasses you need in diopters. The focal length we just found for that lens was 0.75 meters because it was 75 centimeters. So that lens has a power of 1.33 diopters for what that's worth. There is kind of an additional question here which you should try at home, but which I'm also going to show on this simulation because you can see that something actually does in fact happen. What happens if you place the thing that you're imaging closer to the lens than the focal point? So here's the focal point, here's the thing I'm imaging. I'm going to go ahead and move this in closer, 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 closer. Notice, by the way, what the rays are doing over here is that the image is getting farther away, but it also means that these rays are getting more nearly parallel to each other. And when I get right up to the focal point, I basically have virtually collimated the rays going out. Another way of viewing where the focal point is for what it's worth is if you have a point source of light and you place the lens such that that point source is right at the focal point, then you should get a collimated beam out. Okay, so the question though was what happens if I move this closer than the focal point? So the image right now, this thing is at the focal point, the image is off at infinity. If I move closer, here's the image behind it. Whoa, what is this? Well, this is what's called a virtual image. What a virtual image means is basically that the image is not formed by the crossing of any actual rays. So the white lines still represent the actual paths taken by the rays leaving from this point here. And what happens is you can imagine somebody looking out here along some set of these rays. And so they're going to see the image of this thing wherever these rays converge. Well, if you're looking along these rays, they don't actually converge anywhere. but they look like they converge back here. So it looks like there's an image back here somewhere, and that's where you're basically going to end up seeing this object. It's a parent location. And so you'll see a virtual image of the object. And notice, by the way, that the object is now bigger and it's upright as compared with, the image is bigger and upright as compared with the object. Before, when we were on this side, it could be bigger, it could be smaller, but it was always inverted. So I think that's all for today's video, and I hope that you found this extra video helpful for the lab.